first answer questions that I received from students regarding the boundaries. So before we talk about differential pair without a current source. So I talked about if you had the basic idea as we started our discussion is that in a differential pair, it simply means that you're injecting input differentially, meaning that you have separated your signal to two parts so that it experiences the same common mode noise. And then this will be a ground. And this will be VDD. And let's say if this is your output, you're taking out differential output. So the basic idea of this is that I should say without. When I discuss this, we assume that either one of the output, let me just be specific. We assume that VL1 is the sum of your signal, half of your differential signal, times the differential gain plus common mode signal times common mode gain. So VICN plus a common mode gain. So that was our discussion. This is only true, valid, when your transistors are in the correct operation region. So this is when Q1, Q2 are in active. So this is the important assumption. So this means that your output, VL1, if you look at, you can also write VL2, just to be clear. Or we can write down this minus the differential signal plus the average. So I want to tell you that this is only valid when both transistors did not hit the boundary. So if, what happened is that if so meaning that VL1 must be, or VL2, both of them must be within the operation which is lower than VCC. So this is, make it clear, this is VCC. The highest VCC, lowest, is when this device operates in saturation, so that will be VCE set. So if your output is within this range, we assume that our transistors will operate in an active mode. Therefore, this will still hold using small signal model. This is based on small signal model, meaning that your transistor must be in active mode. Okay? So what happens if your signal is too high? What I meant is either this or this. Either one of them, if they're too high, then it would then lead to a saturation of signal. Therefore, when you do subtraction from each other, we'll not be able to cancel it. So that's the limitation as to what are the boundaries of the circuits. So another thing in talking about boundaries, I want to highlight, so let's, so this is without a tail current source. What if I added a tail current source? There's actually two types of boundary. One is limited by your differential pair. The other is limited by the saturation mode. So let me go through an example to explain that. So let's say I'm still using a bipolar. As an example, you can actually do the same analysis considering a Okay, Q1, Q2. Let's say I have my RC equals to, let me get the boundary. I have a tail current source and V in 1, V in 2, VO1, VO2. Okay? So there are various questions. Let me first give the parameters. So let's say my VCC is 3 volts, and RC is 1 k ohm, just to make our life easier. And then I'm assuming that IEE is 1 milliamp. Okay? So I will then ask you to find a few things. One is to, so these are the key parameters. Okay? So one of the key important things is that you want to find out what is your VO, your operation range, which is VO max and VO minimum. You can just simply pick one. And then the other thing is that IC1 max. What are the boundaries? And IC1 minimum. Okay? So this is the first case. Last thing is that we want to know our maximum VL. Let's define VL as VL1 minus VL2. So what is the maximum output swing? What is the maximum difference between the two? So typically, if we talk about maximum swings, you're assuming that you only look at the absolute value because it's just the magnitude of how the margin of the output. So if this is the case, remember we have already done exercise as to plot V. So you should be able to plot this VID as defined as V in 1 minus V in 2. So you can plot VO1 and VO2 individually. So let's say if I want to plot VO1 as a function of VID. So we know that because it's bipolar, we know that it's ID max, VID max. We don't actually need to know the size of the transistor or biasing condition because this will be fixed at about 100 millivolts. So this is minus 0.1. This is about 0.1. So you start with the balance point. We know that the balance point, equilibrium point, that's my equilibrium point, where VO1 equals to VO2 equals to VCC IEE, half of IEE RC. So this will make this point. You should be able to find this. This is 3 minus 0.5. So this is 2.5 volt. So we know that it will start at 2.5 volt, and then its maximum level. So as your input being 1 increases, what happens is that there's more current going this direction, therefore it will drop all the way until all of them, right? So this will be my VO1 minimum, which would then be VCC minus Q1 takes all times RC. So this will be 2 volt. Okay? lowest point will be, I'm not in scale, but this is 2 volts. And then it will rise all the way to VCC. This is VCC. So your VO max, either 1 or 2, doesn't really matter. VO max. Let me just highlight. VO1 max will be VCC, which is 3 volts. So you should know the answer. The maximum level of this point is when this is turned off. Q1 is turned off. There's no current. All the current goes to Q2, so that your highest level is VCC. Okay, so this is VCC. I should say 3 volts. The answer is 3 volts. This is 3 volt and 2 volt. Okay? So another thing is, of course, IC1 maximum, based on this data, we know that maximum current it can take in is 1 milliamp. Minimum current is 0 because it can turn off all. So we could do this without even doing any calculation. The other thing is maximum swing. So maximum swing is your maximum level minus the minimum level. So the maximum level is 3 volts. The minimum level is 2 volts. Therefore, your V out, when this happens, let me plot it. So we know that VO, this is VO2. So VO2 also balanced at 2 volts. This is highest at 3 volts minus lowest at 2 volts. So the swing is this difference. The difference, maximum difference between the two is 2 volts, right? So once you plot this, you should be able to obtain all the parameters needed. Let me make some minimum. I want to make it in scale so that it doesn't look that weird. So this is 2 volt, 1. I'm sorry. The difference between the two is 1 volt. That's 3 minus 2. Sorry. So your maximum swing is 1 volt. Maximum difference output. But the other thing is, let me highlight this. VO. Let me define 2 parameters so that we don't make a mistake. So let's say, so let me ask you 2 things. One is V out max and V out minimum. So V out is the difference. Let's define V out as, so VL max and VL minimum are, VL max is 1 volt. VL minimum is minus 1 volt. Okay? So that finally, the maximum swing, I should define maximum swing as VL max differential minus VL minimum. Maximum, I should differential swing. Maximum differential swing will then be 1 minus minus 1. Therefore, your swing should be 2 volts. Okay, so there are 2 things. One is, if you're only looking at differential signals, the maximum level, the highest level is this, when it's in the negative regime, where VID is in a negative regime where you will get 1 volt, maximum level of 1 volt. This is the highest, this is the lowest. And when it flips to VO2 is the highest, VO1 is the lowest, you get minus 1. So the maximum differential swing will be defined as VL max, that's differential signal, maximum differential signal minimum, that will give us 2 volts. That's why I'm jumping too fast. Okay, so there's 3 levels of things. One is the differential signal itself. The other is the overall swing. What is the overall regime you could swing your output? So it goes from positive 1 to negative 1. Therefore, the total swing is 2 volt. That's the differential, maximum differential output swing. Let me write it down. So this is defined as the differential output swing. Swing will simply means that your maximum level. Okay? So let me come back to this plot. So this is 1 volt, and then 2, 3. So this is actually my ground. This is VID. As I said, the region is 0.1 volt minus 0.1 volt. Okay, these 2 points. Okay, so this is when you see your minimum. The whole following analysis is based on, we know that if I'm swinging my differential pair, the transistor, no matter where it goes, it only has 2 states. The transistor in this operation, based on this scenario, based on this setting, let's say if this setting is number 1. So under this setting, what happened is that your Q1, Q2 will only be 2 mode. One is active, and it may be cut off because you can turn it off. The current just barely just turn off. When it goes deeper, it's simply just turn off. Okay, so it's either active or turn off, so you will remain in this linear region. Your transistors are operating in either active or either cut off. Cut off is fine. It doesn't really limit your operation regime. So let's think about another scenario where what happened is that what if my resistors are larger? So let's say if I give if I increase my loading resistor to 5 volt under the same condition, what happened is that I can also do the same plot. Then the center point will be point times 2.5, it will be 2. So you will actually balance at, based on the same analysis, what happened is that the equilibrium point, let's just look at the equilibrium point. So if this is the case, the equilibrium point will be VO1 equals to VO2, which will be VCC minus IEE half times RC. So this will be 3 volt minus this is 0.5 times 5. So it will give you a very low voltage. So what does this imply? This implies that your starting point, your equilibrium point, will be 0.5. So let's look at how it works. So if you increase your voltage on Q1, what happens is that it's supposed to drop. But it drops to, this is if I'm trying to plot VO1. So what happened is that there's a limitation as to how low it can go. So what limits as to VO1 or these 2 voltage? What are the limitations? The minimum voltage, if I'm only looking at a single branch, a minimum voltage, VO minimum, let me use this plot. Let's just look at for Q1 to be active. If I'm looking only on the left half, so this will be the voltage VP, and then I have, if I cut it in half, this is, never mind. It's not cut, otherwise it will be confusing. Okay, so there's a voltage where we'll allow this current source to be to be functional. So if I have a current source, let's just change it into a real circuit. So if I'm implementing this current source with a current mirror, let's say VB, if I'm implementing a current source this way, so VP, there's a potential at this emitter, as this is VE. So if you look at VO1, the minimum level of VO1 so that Q1 will be active will be a voltage across this. This is VCE set. And this is another VCE set. So VCE set of Q1, and maybe this is Q4. Okay? So to make sure that this circuit will still be functional, your VO minimum will be VCE set 1 and VCE set 4, let's say. This is VE minimum. So this is the lowest for that this will still serve as a current source. And this will be the lowest where Q1 will still remain active. So for this two transistor to remain active, I should say, for this circuit to be functional, both has to be inactive. So to ensure that both of them are inactive, you need to make sure that this voltage needs to be at least 0.4 volt. This needs to be at least 0.4. So this will then limit, this will then set to 0.8. So this simply means that at equilibrium, you will actually, if you try to make it into equilibrium, what happens is that your Q1 and Q2 are no longer inactive. So they no longer follow the linear trajectory there is. So it means that if I'm simply putting RC to 5 volt, your transistors are, so you have to consider Q1 and Q2 in SAT. This simply means that if I'm doing this at equilibrium point, I'm already in saturation. This simply means that my V out, VO1, will be, let's say if my Q4 is still the same, so I would then be in 0.8. The minimum it can go is 0.8. So we'll no longer, even at equilibrium, we'll no longer reach the target level. So the way to think about it is that you then have your seesaw sitting in a stuck by the single branch itself rather than the swinging of the limitation. So this is just to tell you that for this to be valid, you want to make sure that all of the swinging of you're not touching the ground. So you want to make sure that if the swinging of your seesaw is limited by the swing itself rather than some other limitation, you want to make sure that it's above ground, so it does not hit ground. So in this case, it's already hitting the ground. It's already sitting under the ground, so it's not actually functional. So you want to make sure that your VO minimum will be larger than, so we already established that this is the limit VO minimum, which is limited by Q1, Q2 in set. So that's to say this is 0.8. So anytime you're entering lower than 0.8, meaning that you're hitting the ground, so your swing is not functional when it's sitting down to the ground. Okay? So you want to make sure that in order for it to swing properly, you want to make sure that it's VO minimum, VO1 minimum, or VO2 minimum has to be larger than your minimum level, which is 0.8 volt. Okay, so this is the examples that if I set my swing, this resistor too large, meaning that I'm making it too loose, it will then set on the ground. Therefore, it will not be functional anymore. So we want to make sure that your minimum is always above 0.8 in order for this circuit to be to well functioned. OK， 所以我稍微讲一下这个概念，就是说，如果你的跷跷板就如果你的跷跷板正常可以摆荡最大范围是由跷跷板本身去限制，就是这个电阻去限制的话，那你就要 make sure 说它不要压到地板。那这个就是压到地板的 case。如果你不想压到地板，就卡住了，所以这个就是卡住。所以呢，你要 make sure 说它不要卡住，所以你要 make sure 它在地板以上，它是 above floor by at least 0.8. So this is the minimum it can go. Either it's limited by how far you're away from the ground. Okay? So lastly, I wanted to go through another example. So to get you a sense as to the variations of differential pair, I have spent some time last week on the discussion of using an active mode to implement, I should say, to allow the gain to be maximum. Remember, we have a differential load, a current mirror load. But I discussed with Professor Huang, we're probably not going to cover that in the finals because it will be too complicated. So I'm going to focus mostly still on resistive load. So our discussion or our exams, either on quizzes or finals, will be limited to resistive load. So let's talk about possible ways of implementing resistive load or how one analyzes different variation of that. So sometimes you will see, okay. So I have discussed one of the problem of a fully differential. Let's say if this is my I'm just going to talk about some different ways of implementing differential pair and addressing different type of problems. So let's say I'm trying to build my fully differential structure through this differential pair. Okay? So as we discussed, one of the key important ideas of implementing this is that you need to have a match device. So in a match device, what happens is that you're assuming that your common mode gain. So let me write it down. So VO1. So we're going to consider one case when there's match, when they're matched, meaning that both transistors are the same, ID1, ID2. Let's say I'm only looking at resistors where there's mismatch. ID1 equals to ID2. So what happens is that if I have matched transistors, a matched load. So if you look at VO1, which would be a differential gain, one have VID, and VO2 will be a differential gain times VID minus VID plus a common mode gain 1 VCM, common mode gain 2. So this is from the left branch, this is from the right branch. If they're matched, they should be the same. So if I want to write it down, if I actually really cut it in half, and so your common mode gain will then be 1 plus 2 GM RSS GM RD 1. let's just give a general equation. So let's say if I have RD1, RD2, we're going to discuss the two conditions. So the right branch will then be GM RD2, also 2 times GM RSS. So let me give my assumption. Let's assume that M1, M2 is matched now. That is to say GM1 equals to GM2 equals to GM. And then ISS has an output resistance of RSS. That's basically what we can use to get this conclusion. So if I'm actually looking at my differential output, as we discussed before, if I have a differential output V out as VO1, 2 minus VO2. This will then give me AD times VID. That's the differential component. So what is left in the common mode component? Sorry, I made a mistake. Okay? So the common mode component will be okay? So if your common mode gain from the left and the right is not exactly the same, meaning that you will not be able to fully cancel. So then your common mode gain will become the new. So there's two conditions. One is if RD1 equals to RD2 equals to RD, so then ACM1 equals to ACM2 equals to an ACM, whatever. If they equal each other, what happens is that your output will be AD, VID. So in this case, we should say that common mode noise is fully canceled. Okay, so you could, in this case, we can assume that its common mode gain is 0 because you don't actually see any amplification. So you can rewrite it as this equals to ACM plus VICM, where this equals to 0, right? Your overall V out differential output will then give you that. But what if it will not be exactly the same as I said, even though you get identical twins? There might be some difference in heights or weight or slight little differences, even though you try to make them the same. So what if ID, let's say ID1 equals, RD equals to R, RD1 equals to RD, RD2 equals to a small difference. So you're assuming that the two resistors are not identical. That's very commonly seen. So what happens is that you can do the same exercise, and then we can find out that my output will then become AD. I'm doing the same exercise, just inserting two different common mode again. So what I get will be, let me get the equation. So what we eventually get is GM delta RD 1 plus 2 GM RSS times VICM. So that is to say, if your fully differential architecture, even though I'm doing fully differential, I'm assuming that if they're identical, they can cancel. But if there's some mismatch that slips in, this is typically referred to as a mismatch that actually occurred in your circuit. then this will then come into your circuit to cause a non-zero. This will be your common mode gain. Your common mode gain will then becomes will be injected because of a mismatch between pairs. Okay? So if this is the case, let's look at what is common mode rejection ratio. In the previous case, if it's fully matched condition, we know that if this is fully matched, this is matched. When loading is also matched, what happens is that your CMRR will be infinite. So let's look at if there's a mismatch, what is the common mode rejection ratio in the case underneath? We know that on the left, this is minus GMRD. So that in a mismatch cases, this is when there's mismatch. Delta R. Just to be clear, even though it's still fully differential, but there's a mismatch in your circuit, then this would then lead to a CMRR, which is GMRD divided by GM delta RD 1 plus GM RSS. Okay? So if you rearrange it, this will be, this is the attenuation factor from the degenerate current source. And then, so to improve your overall gain, overall common mode rejection ratio, even in fully differential architecture, what you need to do is still the same. You want to improve, still want to improve your current source or the suppression of common mode gain. So you still want to improve this factor, which is the suppression of common mode gain. And then you want to make, what's my color? Make it as matched as possible. So there's two ways of further improve if you have this. In the real design, what is the two direction? One is to make sure that you attenuate the common mode noise gain still, even though the single end common mode noise and the gain, and then to make sure that your device is more matched. Okay? So once we have this understanding, you will then see why we would like to, the point of making a twist. So the point of, the problem of having this mismatch is because you have two transistors. So two resistors, the two resistors may not be identical. So one of the ways to resolve this is to use only one resistor. So I'm going to give an example. You can actually go through the textbook. They have different examples. So if you see these type of examples, you would then get a sense as to why they're doing this. So I have a differential pair with a single load. So if you're looking at, let me just give an example as to the type of circuit it will look like. So the circuit with single load, one of the examples will look something like this. So these current sources can be made very easily through current mirror. So instead of having an independent load, let's say if this is ISS, I'm making this half of ISS. This is half of ISS. So instead of having two load, I'm creating a, I'm adding, I'm just going to use right above here. Rather than having one, rather than having two, I'm using one. So what does this mean? If you have this type of circuit, what happens is that it's equivalent. I'm going to just let you think about it. At equilibrium, what happens is that the current, the level of this output would then be balanced. Therefore, your equivalent level, there's no difference, current difference. When making sure some of the currents coming down, more current coming down, then there will be current bridging. Let me write down two conditions. One is that if when Vin, this is still a differential pair, so when VID is larger than 0.1 volt, what happens is that you suppose all the current goes from this direction so that ID2 ID2 equals to 0, ID1 equals to ISS. Okay, so this is, so if you think about this scenario, this is when there's no current, 0, and this would then take in ISS. So the current's flowing from here to here. This is in condition 1. So in this case, your VO, if I'm defining my V out, VO1, VO2. If I'm dividing my V out as VO1 minus VO2, this will be my differential output. At this location, it will simply be half of the current, all half of the current, times RDD. Okay? This is condition 1. Condition 2. I'm just going to use the blue. So this is VOD is defined as VO1 minus VO2. Because the current's flowing in this direction, therefore you get a minus sign. Minus 1/2 the current RDD. Okay? So what if, let me use the right color. So this is VO1, this is VO2. So the second branch will then be if VID smaller than 1, smaller than minus 1, minus, or smaller than minus 0.1 volt, what happens is that the current would then be, this would then be turned off. This would then be turned on. This will take all the current, ISS, because it's more minus on the right-hand side. This will be 0. So what happens is that then you would then have this current come in to contribute so that it will reach ISS. So in this case, ID2 equals to ISS. ID1 equals to 0. So that your VOD, so the current is flowing in the opposite direction, the same amount of current, which is 1/2 ISS times RDD. Okay? So this will then allow us to use only one resistors. Therefore, your virtual grounding would be half of RDD. So it's equivalent, if you want to think about it, this is the large signal range. If you want to look at it as an equivalent circuit, its equivalent circuit will be, let me use this. The equivalent half circuit for differential if your equivalent half circuit for differential operation will be the center point, so it will be 1/2 RDD VID, half of VID VO1. The equivalent, I should say, the equivalent circuit, this should be, if you think about it as, this should be virtual ground, AC ground. So this will be your AC, I should say differential AC ground, will be at the center of the point. So you would then have two virtual ground point. This is VP, and then center of this, if I cut it in half, if I view this resistors in half, they can be constructed as two halves, right? So this 1/2 RDD, this 1/2 RDD. So this point, there will be 2 points, 1, 2. Both can be viewed as a differential virtual ground. Virtual ground signal, virtual ground point to the differential signal because it doesn't change whether it's flowing one direction or the other direction. This is balanced at a particular level for differential signal. So then the purpose of having this type of structure is then there's no mismatch. Because I only have a single resistor, therefore, you can actually have a much matched structure. However, you still will experience mismatch from transistors, but there will be no mismatch on resistors if you want trying to reduce the element to reduce injection of mismatch points. Okay? So finally, let me make a summary. We know that this doesn't function, so we don't actually need this. So I want to just remind you what are the key points you need to take home on chapter 10 on differential pair. So I'm just going to make summary as to the key points one needs to know. So one is that you have differential signals, either VID, VOD, which is mostly what we want for signals. We want the signal to either come in differentially. Your output can be either differential or single end, but for fully differential architecture, you want to have differential signals in, differential signal out, so that to keep your signal most clean. And then we have input common mode, VO common mode. These are noise. So this is something that you cannot control because it's coming from your signal source. But what we want to do is to suppress, to make this as small as possible. You don't want it to propagate. So you want to make sure that this to this will be suppressed. So that is to make, this simply means that we want the common mode gain to be at least smaller than 1. So typically its differential gain is typically determined by the structure. If I'm using a resistive load, its gain is either GMRD or GMRC, depending on either it's a bipolar or MOSFET version. But what happened is that you wanted to still have your significant voltage gain. But then we wanted to reduce. We want to make our common mode gain at least smaller than 1 because you don't want it to propagate, but ideally approaching 0. So this is the minimum you wanted to do. You want to make sure that at least it's smaller than 1, but ideally you want it to be approach 0. This is ideal. This is at least. Okay? And then last thing you need to do is that you need to make sure that you can plot these transfer curve at least to find the boundaries of each terminals and the maximum swing, that sort of thing, is being limited mostly by this structure. If you look at this, this is limited by, as I said, limited by IEE, RC. These are the two parameters which limit how much it can swing. And this is actually the swing which is limiting your boundaries. As long as we're not hitting the blue part, the swing will then determine the maximum output and input range. Okay?